Good day once again, everyone, and thank you for joining us for our short course on multi-component seismic technology. My name is Rodiat Amuson. I'm going to be your moderator today. I am currently in my fourth year studying applied geophysics at the Federal University of Technology, Akure, and I'm also currently serving as the president of SCG Futa chapter. So, our instructor today is Temitayo Folami. Temitayo Folami is Europe Geo Solution business owner for Schlumberger with over 13 years of extensive experience in seismic data processing and imaging, project management and business development in the energy industry. As the geophysics domain champion, it works with clients in the region to understand their technical challenges and needs for effective service delivery. A strong belief in collaboration, leveraging knowledge and skills to create value and win-win situation. Temitayo enjoys mentoring and coaching young geoscientists. He is passionate about helping people and volunteers with some charity organizations in the UK to feed the homeless, mentor teenagers and youth, and provide support for job seekers. Temitayo Folami also graduated from the Federal University of Technology, Akure, and in the Department of Applied Geophysics. Thank you so much, Temitayo Folami. You have the mic.
All right, thank you, Rodiat, and thank you, SEG Futa, for this opportunity, and I hope you can all hear me. Yeah, just give me a thumbs up if you can all hear me on the chat group. Yeah, okay, great. Thank you very much. Okay, so I'm gonna make a start. Thanks for the introduction. Like she said, yes, I finished from the Federal University of Technology, Accra. In a minute, I'm going to go through my profile, but just let me know if you can see my slide. Can you see the full slide?
Yeah, of course.
Yeah. That's good. Yes, so I'd like to welcome everybody. And like she said, we'll be looking at the basic introduction just to the multi-component seismic technology. Yes, my name is Temitayo, and I've been working with Schlumberger for about 13 years now in different roles. But today, looking at the general objectives of the course today, so we'll try and familiarize ourselves with the subjects of multi-component seismic from a theory perspective. And then one of the things I would also do is to discuss some benefits of the PP and PS processing. If you don't know what PP or PS is, you would know in a minute. And then I would try to touch on relevant current and future technologies in the space. Okay, so this is the outline of some of the things that I would be talking about. First, I would give a sort of quick overview of what multi-component seismic is really all about. But then I would do a dive into the seismic market for those of us that are geophysicists or who are interested in coming into the energy industry, for you to understand what the market is like out there. And then I'll come to talk about the acquisition, and then begin to come into more specific topics around near surface characterization, statics, the multiple shear wave splitting. I won't dwell much on the imaging aspect because that's another that could become a course in itself, and I would be happy to come back and discuss more around velocity model building and things like that. And then I will look at more case studies and case studies, and examples of some of the multi-component processing examples that we have out there. Okay, so the introduction has already been given about me. So I've spent the last 4 or 5 years in a role as a sort of client engagement, sort of capacity or business development capacity within Schlumberger, still promoting the business side of things around the seismic processing and imaging side of the business. In terms of data processing, I've had the privilege of processing data from the North Sea, all the sectors, offshore West Africa, onshore Ethiopia, and of course, offshore Central Africa, since I started my career. And I started off in Malaysia, and I'm currently based in the UK. Okay, so what's multi-component seismic in a nutshell? Now, if you've got any questions as I proceed, please do have it in the chat, and hopefully, I guess Rodiat will help me note those questions. Be kind to go very easy on me, guys. Don't ask very difficult questions. Okay, just feel free to ask your questions, okay? And I will try to answer that as much as I can. So let's look at multi-component seismic in a nutshell. So when we talk about multi-component seismic, this is a very interesting topic. I remember when I joined Schlumberger around 2009. At that point, it was just the technology was just picking up. There were a few projects that were running, a few bits and pieces in different places around the world. But then it was still in its development phase. But when we are talking about multi-component seismic data, that helps provide better characterization of the surface than just the P-wave data that we may have from the conventional towed streamer data. So there is a lot more information that we can get. And just looking at the diagram you have there is basically recording more data, still deploying the same equipment, but recording more data. So again, bringing us back to the basics, which would help us in today's class, if I would call it that way. And I know some of us are very familiar with this, but it's really going to be helpful for me to go through this again so that I don't make too many assumptions on what we know and what we don't know. So there are two major wave types. There are the ones we call the body waves, and there are those we call the surface waves. Now, the surface, the body waves, we are familiar of what we call the compressional or P wave and what we call the shear or the S waves. So you'll be seeing me using more of the P or the S wave as I continue. And when we are talking about the when we're talking about the compressional or P wave, you see the particle motion and propagation of these waves, okay, is parallel to the direction of the wave propagation. And I want you to note that. That's really very important because the characteristics of these different waves will then help us understand how they behave with regards to what we are trying to image within the subsurface, okay? In the shear or S waves, the particle motion is perpendicular to the direction, okay, of the wave propagation and is constrained to the plane of reflection, okay? So in the case of the S wave, there is no volume change. But when we are talking about P waves, because it's compressional, there is a volume change, okay? So when we move on further, again, just a quick reminder, right, between what we would experience between the pressure and the shear waves. Again, the P wave, there is deformation, there is volume and shape change. But when it comes to S, the shear wave deformation, we only see a change in the shape only, okay? In the shape only. Again, I'll begin to explain what these things mean, but again, this is a quick reminder of some of the basic things that we might be familiar with. Again, some of the things that you will hear me talk about is also stress and strain. And this is really looking at this concept of elastic moduli, which I will be coming to. Okay, But again, just a reminder that there is what we call stress, there's what we call strain. And just a reminder about the Hooke's law, where stress is proportional to strain for elastic materials. Okay, this is really very important concept that would also be bringing up in this discussion. So maybe you might want to, if you want to take a screen grab of this formulas, you can do that. But I'm not going to be going to any mathematical derivations in this course. But just important for us to be aware of this. Now, when we come to the types of strain, there are 4 that I've got on the screen here, and there are reasons why I'm bringing this up. Now, when we are talking about the longitudinal strain, it is defined as the ratio of change, okay, in length of the material due to the applied force to the original length, okay? This is when, okay, the stress, which is the external force per unit area, is applied on a body, such that this deforming force causes a change in the length, and just in the length alone. And that causes the body to exceed its elastic limit, okay? Now, there is also the concept of the bulk strain as well, which is the ratio of change in volume to the original volume under a normal loading condition, okay? And then there is the other important one for you to know, which is the shear strain, which is the ratio of the displacement to an object's original dimension, okay, due to stress. So it's really talking about the amount of deformation that we see occurring due to a stress being applied, okay, to an object. And there are 4 elastic moduli that can be defined as a result of this, okay? So this brings us to another concept, which I would like to highlight very quickly, which talks about the elastic moduli and things like the Young's modulus and the bulk modulus, the shear modulus, okay? Because there is something I will be highlighting soon that will be relevant to some of these things we are talking about, because for a given material, there can be different types of modulus of elasticity, okay, depending upon the type of stress that is being applied, okay, upon and the resulting strain produced, okay? And one of them is the Young's modulus of elasticity, okay, which corresponds to the ratio of the longitudinal stress to the longitudinal strain within the elastic limit. Now, let's move away from here and begin to go into what we are talking about. Now, I want you to pay attention to this table, because this would help us. This would form the foundation to some of the things that we will be talking about today. So P wave velocity now is a function, which is the compressional wave velocity, is a function of the medium's density, shear modulus, and bulk modulus, okay? And it's important to note here that the bulk modulus is sensitive to fluid compressibility, okay? Which makes the P waves highly sensitive to rock's fluid content, okay? So the dual dependence then of the fluid compressibility and shear modulus allows the P waves to propagate in both solids and liquids. Okay, this is why I'm spending some time to go through this basics, okay? So the shear velocity, on the other hand, is a function of the density and shear modulus of the medium. So in this case, you can see then that the shear wave is insensitive to a rock's fluid content, okay, in any given formation. So within any given formation, the shear wave velocity and reflectivity remain unchanged, whether the formation contains gas, oil, or water. So S waves can travel only in a media with non-zero shear modulus. So they can originate and propagate only in solids. Okay, you can begin to then pick again what those important differences are or characteristics are between these 2 types of waves, because they form the very basis of what we are trying to explore and exploit in multi-component processing. Okay, and then there is also the surface waves, which we call the Rayleigh and the Love waves. Okay, now traditionally within the industry, we've always considered these types of waves as noise within the data. We often regard this as noise, but over the years, we are beginning to find out that they contain actual useful information of the subsurface that we can then begin to put to use in multi-component processing. Okay, so surface waves are generally lower in velocities than the body waves. Okay. All right. So one of the other things that we would begin to talk about, okay, is polarization of the shear waves. Okay, the polarization. And I want you to look at this for a minute, where you have the vertical and the horizontal polarization, what we call the SH and the SV. The P, we know the particle displacement is parallel, okay? But in the shear case, the characteristics of how it propagates also begins to give us some benefits of what we can exploit in terms of subsurface imaging, which I'll be coming to in a minute. But let's leave this for a minute. And I'm going to come to this, okay? And I want you to pay attention on what you've got on the screen at the moment. Okay, so when we go back to the compressional waves or P waves, okay, these undergo partial conversion. And this is what you can see there, where the incident wave, as you can see my cursor. So whenever the P wave comes, which is the incident wave, it usually undergoes what we call partial conversion. So shear waves are this very subsurface interface and can be detected as S waves by sensors, okay? This is now recorded waves that, now these waves, right, they started off as P, but now you have the reflected S wave, you have the reflected P wave, which is what we'll call VS and VP. And then we have the transmitted, right, P waves and the transmitted S waves, okay? So that's really very important. I want you to take note of that. So the recorded waves that start as P waves and get converted to S waves are what we'll call converted waves. I want you to note that down, okay? Waves that start as P waves, but then undergo conversion to S waves are what we call converted waves or PS waves, okay? So P to S, we call it PS waves. In some other literature, you might see C waves, okay? They might call it C waves or converted waves, okay? And then P waves that reflects as P waves, okay, are called the PP waves, just to avoid any sort of confusion, okay? So those are PP waves. Incident as a P wave, coming reflecting as a, and then reflecting off as a P wave, okay? So that's PP waves. So we've got PP waves and we've got PS waves, okay? So the direction then of the travel of the P and S waves means they have to be detected differently, okay? Because P waves can be recorded by single component geophones that can detect vertical motion, okay? Geophones usually are designed to detect vertical motion, okay? When placed either on the seabed or on land, okay? And this can also be detected by the hydrophone, which is a pressure sensor, and it is scalar. On the other hand, the geophone is a vector, okay? It's vector. So it's the direction, it's very key. Okay. For pressure sensors, it's a scalar. Okay. And this will come to in a minute. So S waves, on the other hand, requires geophones then that can detect more than just the vertical component. Okay. It can detect more than just the vertical component. Remember, S waves are transverse waves. Okay. So which will make them three-dimensional in nature. So we would need at least 3 component sensors to record them adequately. And I want us to note that. So the use of more than one receiver to capture both the P and S waves is what we then begin to refer to multi-component seismic. Okay. So we're now getting into the interesting bits of today's talk. Okay. So one other thing you can see on the screen there is I've left an image of a typical sensor. One of the things you have in that sensor, okay, is what we call the hydrophone, which we'll come to later. But then we then have the vertical component, we have the horizontal component. Okay, we have 2 components, which is the XY sort of components, okay, which would be used in recording the shear waves. Okay, and something to also note here is also the velocity profile. Okay, the typical velocity trends for the P wave and S waves. The S wave is much slower than the P wave, and that's what we're just talking about here. Okay, and there are still a few things I'll still mention, but let us continue. We'll come back to this in a minute as we continue, and I'll keep reminding us of some of these basic concepts as we continue. Okay, so one of the things that you will then see, now I want you to pay attention to this diagram. Okay, CMP here means common midpoint, and CCP here means common conversion point. Okay, common midpoint and common conversion point. So for P waves, the angle of reflection equals the angle of incidence, so which means it's symmetrical. That's for P waves. They are symmetrical. And this helps a lot. It makes acquisition, it makes processing, seismic data processing very easy, because we can easily work with that assumption that they are symmetrical. So what we do is that we use common midpoints. So that means common midpoint is halfway between the source and the receiver. Okay. For PS waves, on the other hand, the S wave angle of reflection does not equal the P wave angle of incidence. Okay, so it is asymmetric. It's asymmetric. Okay, which makes it very difficult then, because the assumption we have in the conventional processing of the P wave then no longer holds. It no longer holds. We are not talking about CCP points, right? So S wave always reflects more vertically because the propagation velocity, okay, of S waves is less than the P wave. So this throws in a bit of a challenge and complexity to how we then begin to handle the S wave. Okay. So why multi-component seismic? Why multi-component seismic? So there are a few things we're going to go through here, and I'm going to touch on some of the key bits here in today's course. Okay, so one of the first things I would like to highlight here, one of the benefits of why the industry sort of started moving towards multi-component seismic, and we see that picking up today. Number one is lithology and fluid characterization. We are able to exploit the characteristics of the P and S waves to better characterize our lithology and fluid. One other thing that we also see as a major benefit is fracture characterization, especially in areas where you have fractured reservoirs. Okay, fractured reservoirs. And we're going to come to this later on, because when operators, oil and gas operators, then we need to go on well campaigns, drilling campaigns. It's important that they understand this, especially if they are dealing with a fractured reservoir. So fracture characterization, multi-component seismic helps with that. In terms of subsalt and subsalt basalt imaging, there are benefits to that. And again, I may not be touching on this extensively in this course, but it's something I'll be happy to come back and talk to you about. PS imaging low impedance contrasts. Yes, those are some of the benefits based on the characteristics. So there are certain lithologies that, or pinch outs that may not be picked by the P waves that may be potentially picked by the S waves. Okay. And imaging through gas, again, that's one of the benefits of multi-component seismic, which I will touch on in a minute, because in cases where you have shallow gas, that drastically actually lowers the overburden PA velocity. So that in a way disrupts transmission. So for just P wave only, where you've acquired P wave only, it's possible you find where you go, we call gas clouds. So there's nothing being imaged where you've got the clouds, because you are not, it's not able to penetrate through that formation. So the imaging is obscure. Okay, in that sense. Okay, we also have the shallow resolution, which I'll be talking about, which it brings, and then multiple removal, which is a very important, another important key thing that we benefit from multi-component seismic recording. Okay. So yes, so these are some of the reasons, some key benefits of why we acquire multi-component, and we are beginning to see this gaining a lot of ground, and companies are thinking more and more about acquiring multi-component seismic over the conventional sort of towed streamer technology that we have in the market today. Okay. All right. So when we are looking at multi-component seismic acquisition systems, I just wanted to highlight just a few things that we have in the industry today. So there is the seabed multi-component technology, where we talk about OBC, which is the ocean bottom, okay, ocean bottom cable, and OBN, which is ocean bottom nodes. Okay, we are seeing more of the OBN in the industry today. So they are just nodes sitting on the seabed. So more of 4C, call them 4C, 4 components, majorly for seabed, and we're seeing more and more of this in the industry today. Okay, so you'll be seeing a lot of what I'll be talking about will be tending towards the seabed examples, but whether it's seabed or land, the principles remain the same because it's sitting on the surface. The only difference is that there is a water layer that needs to be accounted for in that case. So you'll be seeing me talking more around the seabed. There's also the land as well, where we're already seeing multi-component. I mean, in this case, we see more of 3 components because hydrophones are not used on land. We only use geophones. So you see more of the 3 components in this case. And we are beginning to see more and more around borehole geophysics and acquisition around 3D VSPs. Okay. And one that we see more around, say, North America. I've heard of this is the 9 components. I've not processed 9 components data, but I do have colleagues who have processed 9 component. I could imagine how that looks like, but yeah. So there are 9 components technology, okay? And under the seabed as well, there is what we call permanent. So they are more monitoring systems. So for producing fields, we have this multi-component cables sitting on the seafloor, and they keep recording data from those, and then they bring that to the surface and it's processed just to monitor production, to see where the changes are with time. So this is what we call time lapse seismic. So we see that more and more being used by the likes of Equinor, the Aker BPs, the BPs, use this technology a lot. Especially we see that in the North Sea as well, where I'm pretty much familiar with, which is usually very interesting when you process these data sets and you can see how the reservoir is changing with time based on hydrocarbon production. And then they can plan the next well or enhanced oil recovery campaigns around this. Okay.
Mm.
All right. So what's the seismic market like? What's the seismic market like? Okay, so at the moment, the seismic market is estimated as of 2021. Looking at the 2021, we don't yet have the figures for 2022, but 2021 is about $4 billion. Okay, estimated of about $4 billion, and we see a 5% change considering the whole COVID thing and all that. So there's a possibility that we might see this increase in the coming years. And I've also given us information by region. So this is just looking at the seismic market altogether and seeing that by region as well. We see a lot of activity in Asia Pacific. And you could see that from 2022 upwards, you can see that the market there will be going over $1 billion in terms of seismic. And we see a lot of activity as well in North America and in Europe as well. We see activities decreasing in Africa. It seems to be fluctuating in Africa, but yes, so that's the market as it is at the moment and the forecast of what we tend to see in this market. But when we look at the multi-component seismic market, just looking at the ocean bottom nodes alone, this is estimated to be about $1 billion of this current market. So if you look at that, you're looking at say 25% of the current market. Okay. But when we look at that with the land multi-component and everything else around multi-component, I personally estimate that the market we currently have at the moment is between 35 and 45% when compared to the traditional tool streamer market. Okay, so this is really very important because we are seeing more and more companies now, even in the multi-client sense. So when I say multi-client, when companies like PGS go out and shoot over an area and then they can sell the data to multiple clients. So traditionally, we've seen more of tool streamer, but in this space, we are now seeing people going out and even looking to shoot multi-component data even for exploration. Okay, and for multi-component business. So we are seeing more and more of these activities in the market today. So if you to become a complete seismic data processing geophysicist at some point in your career, you would be processing multi-component in some form. Okay, and these are some of the top players that we have in the industry today. I've only mentioned a few there. There are other smaller ones that I may not have included here, or someone, yeah, that may not have included here. Okay. So that's the market for us. So let's look at the acquisition very quickly. So the 3-component land acquisition. So like I told you, we have the vertical components and then we have the X and Y, or the horizontal components where we acquire data, and the source here is the vibro-size vehicles that then for this acquisition. Depending on where it is, there are still areas, maybe, yeah, they are using vibro-size majorly in this case. Um, so yeah, this is just an example of planting and harvesting some of these geophones. We now even have very fancy, more advanced type nodes now that are easy to place very quickly on the surface for survey for acquisition efficiency, and a lot of that in the industry. So if you go to some of these companies and you check their website, you will see a lot of technologies around some of these new acquisition systems. I was at the EAG recently, and it's just so new things that are coming up just to reduce acquisition time, okay, efficiency and data quality. Those are the things that the technologies are focusing on at the moment. In ocean bottom cable acquisition, like I told you, these things are draped on the seafloor. So they are the ones that we call the cable acquisition. There is the node acquisition where they are not attached to cables. Basically, they like pods. They are dropped on the seafloor. You can use the arrow. You can use ROVs to place those receivers on the seafloor. So they are positioned on the seafloor. So one of the advantages of OBN acquisition is that you can get this close to existing infrastructure, okay, during data acquisition. Now, when you look at existing oil rigs where they're already producing, it will be really difficult for a towed streamer to come very close. Okay, so what you tend to see is that you see very big holes, okay, where you have those installations and then there is no data being acquired where you really need it. Okay, and you now try to see maybe interpolations being done and things like that. But the benefit you have with OBN data is you can get that as close as possible to the platform. You will still have holes, but very small holes that you can then interpolate compared to ToeStreamer. So that's one benefit of why you have those nodes. Okay, and one of the other things that we are then seeing in the industry from the likes of Shearwater, okay, and some of these other companies as well, is what we call hybrid surveys. Okay, where they are deploying more than one technology. They are deploying both the node and the streamer technology combined at the same time. So they use what we call multi-purpose vessels, MPVs, that is able to handle both streamer and multi-component. So they lay node patches combined with tow streamer configuration spread over the nodes. So this is basically to improve efficiency. It's also very cost effective as well. Okay. And this removes the need for having multiple vessels and crews. Okay. So this is the sort of the future that we are seeing in the industry today, which is getting exciting as well. Okay. All right. Let's begin to get into some of the fun bits. So looking at just in the land case now, which is also very similar to the seabed case. So always remember what we are looking at, okay? It's the vertical, then the X and the Y component, okay? Always remember that, okay? But again, there are a few things we need to note here. So looking at the acquisition systems now, okay, when you have a boat and because you lay the receivers on the seafloor and then you are shooting, the source vessel is then being towed and then it's shooting, right? So one of the things that we must understand as well, okay, my slideshow doesn't seem to be showing here. Anyway, so one of the things that we need to, that becomes very interesting then, is what resolving, after we acquiring in the sense, we need to resolve this into what we call the radial and transverse components. Okay, there's what we call the radial and transverse components. which this needs to be resolved into. I'm hoping that I still have that later on, and I'm not sure if that was another slide that was hidden. Okay, I'm just going to continue. If not, I will come back and address that. So because when we are looking at the radio component, okay, this is usually parallel to the inline direction between the source and the receiver. Okay, and just give me a minute. Let me just confirm that I still got that in my slides. Okay, maybe that is still coming up later on. So I'll be talking to us about the receiver rotation later on. So I think that's still later on. So just for you to visualize this, the receivers are already on the seafloor, and then you're just what the boat is then towing. You have the source vessel that is then shooting. So I want you to begin to imagine this compared to the tow streamer, where it carries the cable and it carries the sources as well, right? That's different. The receivers are already on the seafloor, and then all you're doing is just shooting. So you could imagine the different various directions that data is then being recorded from compared to the tow streamer. And we're going to be looking at the azimuthal coverage and the implications of that as well. Okay, so let's look at data. Yay. So the first data. So this is what we call a common receiver gather. A common receiver gather. So this is some of the things you would hear when it comes to multi-component processing. Okay, that's some of the things you will hear when you come to multi-component processing. So when we say common receiver gather, okay, to help you with that, I've got this diagram up here to help you. So consider the red point as your receiver location, okay? And then you have these various shots, which are the blues, coming in to that single receiver, okay? So it's sorting. So within this, so what you see for this gather is a single receiver with different shots. So you see that from what we call source detector distance. So the farther away they are from the receiver, so this is near zero, right? This is near the receiver, and then farther away from the receiver in terms of distance. Okay, so we call this common receiver gathers. So one receiver with all the shots within the allowable radius or offset. Okay, so this is how a typical I say typical depending on the geology. So this is what we call the pressure or the hydrophone data. This is your X component, this is your Y component, and this is your Z, which is your geophone, the vertical component, okay? So one of the things you can see which has been highlighted here is the P waves on both the P and Z. Okay, you can see that very clearly, which is being recorded by these two components. Okay, and then on the X and Y, one of the things you can see is the converted PS waves on this X and Y components or horizontal components. So this is interesting. So one of the things that immediately stands out to you is that the character of what you see on these four gathers are different. There are some things that looks the same. There are some things that looks different. Different things being recorded, okay? And this is what we do in multi-component this processing. We're trying to exploit, use the various information that are being recorded by these various components, okay, to image the subsurface. Okay, so we're going to come more into this more data. We'll see more data as we continue. Okay, so this is just to give us an idea, okay, of how things. I'm not going to play this video because of time, but I'm sure if you go on YouTube, you would find a lot of videos around seismic acquisition air guns. Okay, so there are P-wave sources, marine sources that are usually used. So that is just for our information. But one of the things I want to bring to our attention here is the options for acquiring multi-component seismic data. and the seismic modes that are associated with each option. Okay, this is really very important, okay, for you to know whether the data acquisition option is 9C to 3C or to 1C. Okay, in each case, we see um, what the source and the receivers are and what the captured modes are. Okay, so the A bit applies to the isotropic earth, okay, in the isotropic case, while the B, okay, applies to an anisotropic medium in which the shear wave splitting, okay, in which shear wave splitting occurs. And the whole idea of doing this is that there are more, just to highlight the fact that in acquiring multi-component data, there are a few thoughts that go into designing the acquisition itself. That's why I'm bringing this up, right? In an anisotropic medium, there are some odd things that come into play that we need to think about. The kind of sources that we use, right? And what modes are being captured in that sort of sense. So again, something for us to note. And there is a reference there that you could look into to learn more about this. Okay. And one of the other things we are seeing in the industry today is what we call the simultaneous source, okay, acquisition. And this is really just to speed up or expedite acquisition, right? Where rather than waiting for one source and then another source, you have the source shooting simultaneously at the same time. And we have within processing, there's what we call the blending, where we are then able to separate out the various shots. Because what you see is that you have the shots overlapping each other. They overlap each other. Again, this is just for efficiency. Okay. And they leave that to us processors to sort that out. So we're seeing more and more of that in the industry as well for efficiency. And then we just do the blending and separate the shots. Okay, so azimuthal coverage, wonderful. Okay, so I want you to pay attention to this. Okay, so on my left is what we have the wide azimuth. Now, one of the things I didn't put here, but which we'll see in the next slide, is what we call the narrow azimuth. But one thing you can immediately see here is the coverage of a typical multi-component data. And that is the fact that it's rich azimuth. It's full azimuth, okay? And the advantage why you have that is because remember, the nodes are on the seafloor. They are ready placed. So when acquisition is going on, remember the receiver guide I was showing you, it can capture sources. It is capturing data from different directions, okay? From different directions. So in a sort of 360 sense, as opposed to if it was being towed behind the vessel, just like the one you have on left, it becomes like a narrow azimuth. It's only in the direction of the boat. That's where you've got your sort of full fold coverage. Okay, so I love this table here doing a comparison of what you have between a tow streamer and HDOBC comparison. So what you can immediately see is what we have in the conventional narrow azimuth tow streamer, okay, or what we call NAS, right? So it's narrow azimuth tow streamer, okay, and you can see what I'm talking about here. The offset azimuth distribution here is very narrow. Excuse me. The offset azimuth distribution here is really very narrow. Okay, so in terms of how you then image the subsurface, you are limited. Okay, when in cases where you have very complex geology, in terms of what you are then able to image or characterize, it becomes very limited. Okay, in a multi-azimuth tow streamer sort of case, you're trying to, what you have here is the boats going in different direction. Okay, it's set to have the worst azimuth distribution. It's not full azimuth and it's lower fold. Okay, again, this is again all these acquisition designs are dependent on your objectives in terms of imaging the reservoir. Okay. And then on the other hand, we have what we call the high density full azimuth HDOBC. So these are all full azimuth distribution, high fold, right? Good coverage, what we call rich azimuth. You love it, right? The wide azimuth is something that is close to it, that which we are seeing in the industry today, which are trying to achieve with tow streamer, but it's more expensive than the conventional one. You see, this requires a minimum of 3 vessels, okay, being mobilized about the same time. Okay, and there's what we call the ridge azimuth tow streamer. This is really expensive, even for any small survey. And even with that, you still don't have the full coverage. Okay, it's like call shooting. They're shooting in calls, right? In cars. They do that in areas where you've got subsalts and things, and they need to image the flanks and things like that, the likes of Mexico, Gulf of Mexico, and they see all that sort of call shooting. Okay. But one of the things you can immediately see from this data, when you look at the tow streamer here on the left here, and you look at the sparse OBC, when we say sparse OBC, it means the receiver spacing is sparse. So there are times that sparse OBCs are acquired due to cost. Okay. So maybe you can see from one receiver cable to another receiver line. Okay. They might be as far as 300 or 600 meters apart. And then from one receiver to the next in the inline direction, might be looking at say 100 meters or 200 meters. So that's really sparse. And then there are high density ones. So when we say high density, it's all in the receiver spacing and in the short spacing, how in sort of the short carpets. Okay. So definitely this is less expensive and this is more expensive. But then you even with the sparse OBC, you can begin to see some of the things, the geologies and formations that have been imaged here that you see hints of it on the tow streamer, but they are not fully imaged, and you are beginning to see that on the OBC. And that's the benefit of multi-component processing. Okay, that we are beginning to pick. So improve frequency content, especially on the low end, which is really helping with this imaging at the reservoir. This is the sort of low frequency there is helping. What you're seeing on tow streamer is type of high frequency, okay? But we are then beginning to exploit the low frequency that the multi-component brings, that we are then being able to image that the sort of steep dip in geology here, okay? So one of the other things we see is multiple suppression, which I will be talking about. And it also helps to image some of these complex structures, as we can see here. And enhanced AVO, which, okay, I will be talking about reservoir characterization in this case, but yes, it helps with AVO, and you can begin to see why it will help with AVO. Okay. Okay. So if you have any questions, please just write down your questions. I'm trying as much as possible to carry us along. Okay. Just give me a thumbs up if you're still with me. Give me a thumbs. Someone is trying to say something, but I can't hear you. Okay. Okay. If you're getting value, just give me a thumbs up if you're still there. Okay, that's good. That's good. That's good. All right. Great. Great. Good. 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 Yeah. So let's continue. So multi-component it's exciting, and yeah, for me it's exciting because when you understand those basic principles, it really helps and is usually fun when you begin to process the data. But there are challenging times as well due to all these complexities that we see. Now, I'm not going to spend time on this receiver location and orientation, but I'm going to just draw your attention to this concept. Again, this is just introduction. Okay. Again, the receiver location, you have the receiver, then you have shots coming into that single receiver. Okay. So that's to note. I think hearing some noise in the background there.
I have a question, sir.
You have a question. Can we wait till the end before you ask your question, please?
Okay, sir. Thank you.
Yeah, please just hold the question to the end. I don't want to get sidetracked because of time. So please just hold your questions if you have any questions. Okay. Thank you. Okay. Okay. So one of the things to remember in terms of vector measuring system, the geophone. So amplitude event is measured fully. Okay. In the vertical case. When it's coming, it's measured, but when the amplitude of event is not measured fully, it's when you have the event coming in at an angle. So we are only able to record only the cosine theta of that event coming in. So so what we are saying is that depending on how this data is acquired in terms of coupling of the receivers on the seabed or on land as well, there might be some corrections that might be required as well to the data in order for us to have that quality, for us to compensate for whatever has been that may have gone wrong in the acquisition. Okay, and the same thing also happens whether it's horizontal or it's vertical. Okay. So one of the other things you also need to begin to understand is the horizontal orientation analysis. So the shear wave motion recorded on the horizontal components can be reconstructed by mathematical rotation, okay, which I mentioned earlier, into what we call radial components and transverse components. Okay, the radial components is the plane of wave the radial component of motion in the plane of wave of propagation, while the transverse component is the outer plane of wave propagation. Okay. So these are some of the concepts that you would be hearing in multi-component seismic processing. Okay. And it's important that these things are compensated for, which let me just quickly go into that now. So there's what we call receiver rotation. Okay, that's what we call receiver rotation. Now, for each of those nodes that you see, they have what we call inclinometers in them. Inclinometers in them. So they give you information on how the receiver is sitting on the seafloor. Okay, so there are two things we want to resolve when we acquire data. We want to resolve, okay, this into radial components and into the transverse components. So when we're talking about the radial response, is the horizontal ground motion in the source receiver plane, okay, and the transverse response is the horizontal ground motion perpendicular, okay, to the source receiver plane. Okay, I want you to note that, and I'm trying to make sure as much as possible that it's simple for you to understand. So looking at the marine case now, which is the ocean bottom, and you have your receiver sitting, one of the things you can immediately see is that depending on how they've been placed on the seafloor, right, it's not all going to be perfect. Okay, and then they leave all that rubbish for processors to you just, to figure out in processing, right? So these things are just dropped on the seafloor. So where that is facing your horizontal components, whatever, may not be all consistent, okay, on the seafloor. So now when data then is being acquired, okay, so when data then is being acquired, remember, in terms of your radial and transverse, remember, one is along the plane of the source receiver acquisition and one is perpendicular to this. So from one shot to the next, this would be different. This would differ. What you call your radial and transverse would differ. This is really very important, please. This would differ depending on where the shot is. Okay, so the radial is always in parallel. It's always in that direction. Okay, the source receiver direction, regardless of where the receiver is. Okay, remember, that's where you would be recording your full amplitude. the full amplitude, okay? And we need to make correction for this in processing, which is what we call orientation analysis. For each shot within a common receiver gather, okay, the three component direct arrival response provides, okay, a normalized P wave polarization vector. So when cross correlated with the hydrophone, okay, so orientation analysis, okay, normally involves determining the rotation of the horizontal components to establish the vertical. Like I said, the inclinometers will be installed in this receiver, so they will help you in this sort of mathematical, in this sort of processing of this data. So an example here is looking at this common receiver, for example. Okay, this acquisition inline and crossline components, the receiver orientation is constant, polarity reversal is near zero. And then you look at this, okay, in the source coordinate system. Okay, the other one we looked at the acquisition coordinate system. Okay, but in the source coordinate system, remember the radial and transverse now. Okay, components. So the receiver orientation is different for each shot. Okay, the receiver orientation will be different for each shot. Okay, so when you hear radial component and you hear transverse components in multi-component processing, this is what we are talking about. So I'm not going to go fully into this so we don't confuse ourselves any further. But again, this is one of the joys of shear wave processing. These are some of the things you have to do upfront, okay, to compensate from your acquisition coordinate system to the sort of source coordinate system. So corrections have to be made to the amplitudes and on all of that, compensating for the orientation analysis and all of that. So let's look at shear on the vertical. So there are times that your Z is not vertical, your geophone is not vertical, or your vertical component is not vertical. Okay, so or there is leakage, okay, in terms of coupling and all that, what we call crosstalk or cross coupling. And so what that translates to, okay, is that you've got your shear noise on the data. Okay, you've got the shear noise on your data. Okay, and you see that more on the near offset, and they are usually like cone shaped. Okay, they are cone shaped, more near offset. I think I jumped one slide. Yeah, I jumped one slide. I didn't want to. Yeah, it's the same. So, but then we have to remove such noise from the data, from the your P and the Z, the shear leaks into the Z. So we have to clean that up. So one of the things we use, so this is one of the Schlumberger toolkits that we have. But what that is basically is you're able to model that shear noise from the other components and subtract it from your Z components, which is another advantage that brings. And when you record the shear noise on your Z component, you can use the information from the other horizontal to try and model that as well and remove. I just thought I mentioned this as some of the things that you would see in processing of this data as well. Okay, again, this is just highlighting that as well on this example, where on the left you can see the data there with a lot of the shear noise. You can see cottony, this cone shaped in the very near surface, and then that is removed, and you see the difference on the far right of what the noise you are removing. Okay. All right, so let's go to near surface characterization. Remember I told you that previously in the industry, we've always removed what with this surface waves, which we call ground roll. Okay, we've always seen it as noise and we've removed it. But one of the things we are beginning to see for a long, at least for the last 5, 7, 8 years now, but it's more routinely done now, is what we call the surface wave analysis and inversion. So you see more of this being done in sort of geotechnical studies, okay, near surface geophysics type of engineering work. So you see this being routinely done around using seismic refraction, acquisition, and some of these things to characterize the near surface. And we're beginning to see this also in the seismic industry, because now we're able to use our surface waves now, that information the surface waves provides to characterize the near surface. Okay, so today we are now making use of this information to characterize the near surface. And we also use this for velocity model building, because one of the key things we are able to get from here is our VS, the shear velocity, that initial shear velocity of the near surface, which we can then incorporate into the velocity model, into our velocity model or geological model. So in this case, what we do simply is a short gather analysis of the ground roll. And then that provides a surface wave dispersion, what we call a surface waves dispersion curve. Okay, and that is decomposing that into phase velocity and frequency. Okay, and this is used during the inversion to build near surface velocity models. Okay, so more accurate near surface characterization then provides the information between the hopples and a better static solution as well, which is what we see at the bottom image. But one of the very things here is the VS model that we're able to get from this near surface characterization, which we can then, that is very accurate, that we can then put into our velocity model building. Okay. Okay, so one of the toolkits we use in Schlumberger is what we call SWAMI. But again, this is just a surface wave analysis type tool. So this is basically enables extraction of the phase velocity characteristics per frequency from the surface waves to facilitate both velocity model building and advanced coherent noise attenuation. Okay, so one of the things we are beginning to now see is that in analyzing this surface wave, we are not only utilizing it to build it, to characterize the near surface. If we can decompose the surface wave, we can also use it in noise attenuation, right? If we can sufficiently decompose that, then we can also subtract it from the daytime. Okay, so it's more like an advanced coherent noise attenuation, because using the same frequency versus phase velocity properties of the analyzed surface waves. Okay, the SWAMI inversion enables estimation and removal of the direct alias and non-alias ground rolls for multiple surface waves. Okay, and then the other thing that can be done in this domain, okay, which is of benefit, okay, is the fact that the first order scattered ground rolls for multiple surface wave modes are also being able to remove. Now, this you cannot do. These types of complex and coherent noise are very difficult for you to remove if you're just using noise attenuation methods that only discriminates based on velocity. Okay, such as your FK filtering and things like that. It's not going to work because of this complex modes. Okay. All right. So this is just a case history where, again, some of the benefits that this provided was the VS velocity field. You know, we had that initial field, noise removal, shear statics, the Q compensation, and the initial model for elastic FWI. Now, that's the full waveform inversion. Full waveform inversion. That's something we use when it comes to velocity model building. Again, that is not covered under this topic, but I'll be happy to do that if that is of interest. Okay, so I'm just going to touch on this. I'm mindful of time. I think I've got about 30 minutes more. So I'm mindful of time. So, but again, like we have in the land case as well, one of the things that, and even it's always statics. It's always static. Statics is always an issue, okay? So this is a time correction from surface to a reference plane, okay? And basically when we resolve for this, what we're basically, it's removal compensates for any weathering zone. Now, when we're talking about weathering zone, this is basically a distinctive layer of weathered material that extends roughly parallel to the ground surface. So, and this differs in content, okay, from the layers above it or below it. It differs in its mineralogical or chemical composition to anything below or above it. And we also talk about the weathering velocity, which is simply that velocity with which a seismic P wave travels through the low velocity layer. Okay, so to compensate for the effects of variations, okay, in surface elevation, in weathering thickness, and or weathering velocity. So that's why we apply statics. Okay, so these are some of the assumptions that we make when we are looking at static corrections. Okay. This is really interesting because we need to compensate for this in processing. So, which is why I'm mentioning it. We need to do this analysis, and multi-component acquisition helps us in these assumptions. Okay, in being able to compose and to compute the statics and remove it from the data. Okay, this is something just worth noting, that there's always a statics component, because remember, this is sitting on the seabed, and it's also similar to land where it's sitting on the land surface. And there's always one thing you must compensate for, which is the statics. And there are ways we compute the statics, which I'm not going into in this study, but again, the benefit comes from the multi-component data that is being acquired, and we can compute the statics and then correct for that from the data. PZ combination. So let's look at the multiple. Let's look at the multiple. And there is a concept we call PZ combination, okay? PZ combination. I'm going to go through this. So one problem of OBN or multi-component acquisition is the water surface multiples. And these multiples are waves which have reflected off the subsurface, and then they've bounced back up and up, bounced back down off the water surface. Okay, so they've gone, they're reflected through the subsurface, they've gone up into the water layer, and they've bounced back again, and they are recorded. Okay, so we call this the receiver ghost. We call this a ghost. Okay, and I don't know why they call it a ghost, but it's the receiver ghost, simply like a multiple. And what happens then is that the receiver ghost and the water layer multiples, they generate notches in the seismic bandwidth. So it begins to limit the usable bandwidth you can use within the seismic, and this needs to be addressed, okay, in processing. So this is why we combine the hydrophone and the geophone data. This is why we call it BPZ, okay. Number one is to suppress the water color multiples, which I'll be showing us in a minute. We also enhance the low frequency. So by adding the geophone signal to the 0 Hertz hydrophone ghost notch. So this in itself cancels out, right? And we are also enhancing the high frequency by reducing the complementary geophone and hydrophone ghost notches. Okay. So so one of the things for us to note, basically, which I should mention, is that the positioning of the multi-component sensors on the seabed actually presents an opportunity here to reduce the receiver ghost and the water layer reverberation sequence because of the difference in the behavior of the pressure wave and the particle displacement on the seabed. So the hydrophone records only the scalar pressure response, remember that, and does not distinguish between up and down wave field. So there are two wave fields I will be introducing to you. One is called the upgoing wave field and the downgoing wave field. Now, the hydrophone, being a scalar, does not distinguish between the two. Okay. The geophone, on the other hand, it records the vector displacement of the seabed, that is different for both the up and down. So the geophone, on the other hand, discriminates. Remember why we spent some time looking at those principles. So it's very important. The hydrophone does not discriminate. The geophone discriminates because it looks at the vector displacement. Okay, and there is this cartoon here just to help us. So you have your reflection coming off this source. It goes into the subsurface, gets reflected here, but then some of that also goes into the water layer, okay, or column, and then it gets reflected back as well as ghost or as multiple, whichever way you will call that. So what we do in PZ combination, or what we call PZ summation, is a weighted summation of the hydrophone and the vertical geophone components designed to determine the vertical propagation direction of the recorded arrivals. Okay. Note that. So what we are doing is summing it, and I'm going to come to that in a minute, but note this what I put here for you to understand. So the pressure does not discriminate. So you have the P up plus P down. The velocity wave field, on the other hand, is a vector. It discriminates. So you have your P up and you have your P down. P up, P down. So this is your P up, P down. I want you to note that. That reflects up to, that's a negative there. So it discriminates, while the pressure does not discriminate. This is really very important for you to note. Okay. So for us to calculate the spectral notches for the hydrophone and geophone, this is the calculation here. Okay. So the other one is half, the other one is 1/4. Okay. So this helps us it gives you a rough idea of where you expect the notch within the seismic bandwidth. So this is the formula that we use. So let's look at the ghost notches. So this is dependent on the source depth. Okay, this is dependent on the source depth. Depending on the depth, that is where it determines the where this is expected. Okay, where the ghost notches are sort of expected. So when you begin to go through 10 meters, 30 meters, 50 meters, it gives you an idea of where you begin to expect the notches between the seismic bandwidth. So as you go deeper, it reduces. You can see how frequent that is now. And this is a diagram pretty showing. So if you know what the water depth is, you can tell. Well, if you know the water depth, you can tell where the notch is expected to be within your seismic bandwidth. Okay, so what we then exploit here is the fact that the geophone and hydrophones they record different attributes. They have different sensitivities. They react differently to multiples and other noise. And that is what we want to exploit here by combining the two information in a sense so that it cancels out. That's the simplest way I can put it, just for it to cancel out. So the geophone data usually tends to be a lot noisier than the hydrophone data. Okay. So what I'm saying is not that simple to some, but for the purpose of this course, I would say what we are doing is to bring them together, but it's not as simple as bringing them together because we have to do something about the signal to noise ratio before we bring them together. We also need to do something about matching the various components to each other, matching the geophone component to the hydrophone, so that in terms of amplitude and all of that, we are combining that correctly. So in terms of calibration, we can use the reflectors to design a scalar to do that, or we can use the reflections, defining the reflection window and to calculate the scalars. But I'm kind of used to the one where we use the refractors in designing the scalars for our calibration. So this is what I want you to see here, okay? So when you shoot your data and that data, that reflection comes down, okay, if your receiver is at the sea bottom, it gets recorded. The moment it gets back to the surface, okay, there is a reflection of there, right? Okay, for pressure, it doesn't discriminate, right? But for particle velocity, you see, it does discriminate that. And then if you sum that, that can cancel out. So it becomes negative and positive. Now, this is what I mean. Okay, in a simplified form, okay, the hydrophone records the downgoing and the upgoing without discriminating. The geophone, on the other hand, discriminates. It discriminates the downgoing. It is negative, okay? And so when you sum it, it cancels out. And then you only have your upgoing data. That's in the simplest form. So that's it. There's nothing as simple as that. So this multiple, a very perfect way of removing such multiples. Okay, but in reality, it's not as simple, okay, as that. Okay, I'm not going to go into this whole schematics, but it's just reiterating what I mentioned. Okay, for the hydrophone and the geophone, depending on how it travels, remember the pressure does not discriminate, the hydrophone does not discriminate, but the geophone would always discriminate. So you can always do this exercise yourself to see the bounces through the water layer and what will happen. Okay, as long as you remember that concept, you will be fine. Okay, the hydrophone does not discriminate, but the geophone does. It is used to suppress this multiple because the vertical geophone discriminates. So we can use that to suppress the multiples. Okay. All right. Yes, I'm not going to go into this, but again, this is an example of what we call CMP stacks. Okay, common midpoint stacks. So, so we have the hydrophone, the geophone, and when we sum it together, so one of the things your eyes will need to get used to is to understand that everything here is not usable. Okay, everything on the hydrophone geophone is not usable because one of the things you will see on the summation is like you will say, oh, but this nice event. So some of that events, oh, I've not got the timing here. But some of the events we've removed here, some of these false bounces here are multiples which have been suppressed. Okay, so that have been suppressed from the false bounce multiple. Okay, a difference in polarity. Okay, there's a difference in polarity, so it cancels out. Okay, when we sum that together. Okay, I hope. Yeah, we are still going to get to the fun bit. So let's see the multiple in action now. Let's see the multiple in action. Okay, a few concepts just to bring to your attention. So this diagram is basically just showing the orders of multiples that we are attenuating with different techniques. So there is the downgoing at the receiver, which is what we are talking about, right? Or what I will call the receiver ghost. So this is your the green line is the main primary event, if you will call it that way. There is the shot, it comes down, it gets reflected, and it gets recorded. Okay. And then the orange one to the left is what we call the source side water layer multiple. The red one is what we call the surface multiple. And there are different techniques that we use in processing to tackle each of these various multiple issues. Okay. So for the PZ sum, remember, it's tackling the downgoing at the receiver. So that's what we remove with the PZ summation output. Okay. There's what we call the WEM output. This is the wave field extrapolation modeling. Okay. And what that tackles in processing is the source side, water layer multiple. Okay. So we use that. So in this case, you're basically using the reflectivity, okay, of the sea bottom here to predict, using this reflectivity of sea bottom to predict what the water layer multiples would then be from there. So if you know what this depth is, it's like you shifting the data, okay, by this amount so that you can remove this delay, okay, in travel time. And then this other one, which is what we call the surface multiple, okay. And for Schlumberger, we call it GSMP, but this is what we call the SRME, the surface related multiple elimination sort of technique, and that is targeted at removing your surface multiple. Okay, so let's look at some data. So this is a nice one showing what your seismic data looks like. So this is the PZ sum. So this is after combining. So when you're doing processing, we process the P component, we process the Z component. Then at a point in the processing, we combine to have PZ sum. Okay, we call it PZ sum data, and that is what we carry through the other processing steps. Okay, so this is the PZ sum data, and you can see the complexity in a geology like this. And this is after applying WEM, and you can see all these multiples. That multiple there is gone, and you can see that multiple there that is gone. With the GSFP, we begin to tackle more of the multiples, and you can see it gets cleaner. And then there is the tau PQ. This is what we call tau. Some of us might be familiar with the convolution. Okay, where we transform data into this is transforming the data into the tau P space or Fourier space. But in this case, this is like a 3D implementation of your tau P. So this is tau P, then Q. Okay, it's 3D in the inline and in the crossline. So we call it tau PQ. Okay, as opposed to some of you might be familiar with tau P decon, you might hear that, but this one is like a 3D solution to that. So you can see where we've come from PZ sum to this final product here of the tau PQ. Now you will be fooled by a lot of this, which is just multiples, which has now been cleaned, and you can begin to see some of the underlying geology and events here, which can then be interpreted. You can see that deep in there, that fault in there, which was obscured by a lot of these events that are cross-cutting, that multiple. You can see these events also. This is the real event, and you can see the reverberations of that, right? And that has been perfectly handled by the WEM, which is taking that out here. You can see that there's multiples, so it's just a multiple of that. Okay. Okay, so again, this is just an example, just showing the results we have from the North Sea. Okay, the multiple. So note the multiple. So what you have at the bottom of the stack data set is what we call the autocorrelation. Okay, the autocorrelation. So as it gets cleaner as well, it tells you whether or not it's like a form of QC to see how well you're doing with removing multiples. So they would correlate, and as you remove the multiples, it gets cleaner on the autocorrelation panel. Okay, so I think I might be, I think because of time, I might be looking to stop somewhere around the shear wave splitting. So this should we've covered a lot of the basic things. But shear wave splitting is one of the things we are seeing for fracture characterization. And we want to see why shear wave splitting. Okay. So one of the things that is important for us to understand is that for us to understand any fracture system in the reservoir, okay, and I told us why we want to do this, okay, because it's important for operators that may want to drill additional wells, okay, or for enhanced oil recovery campaigns. So shear waves can sense the average fracture properties within a large volume, okay, to help determine the average fracture orientation, excuse me, and density. Okay, so this is really very important. And I'm going to come to this. So a shear wave splitting. So one of the things that a shear wave splits into what we call a fast and slow waves. Okay. So after reflection, okay, after reflection at or transmission through a fractured or what we called earlier on an isotropic medium, see, there are different velocities we then have. What we call, you will see what we call S1 and S2, which is basically fast and slow velocity. So this causes a separation. Okay, so the fractal fracturing gives rise to as what we call azimuthal anisotropy. Okay, it gives rise to what we call azimuthal anisotropy. So this is what I said earlier on. So the shear wave is polarized parallel to fractures is the fast. And the shear wave polarized perpendicular to the fractures is what we call the slow shear waves. And this is how we are able to characterize the fractures, exploiting these attributes. We're able to characterize the fractures. Okay, and we also correct for this, especially where you are dealing with fractured reservoirs, or in areas where there's been subsidence. There is a field in the North Sea where there's been subsidence. As the field is producing, there is subsidence. It's inducing subsidence. Okay, in that sort of system. All right. And we needed to compensate for the shear wave splitting because what we are seeing is the azimuthal anisotropy. So what we would then do when we correct for that, events gets flatter, right? Because there is dispersion. And what we are trying to do is to try and correct for such dispersions. So one of the things you will be obtaining from that is what we call fast and slow shear direction and lags. And then we compensate for those lags, okay? And with that could input into what the geomechanics guys would do as well, where they study for fracture characterization, using other properties of rock and things like that. So we correct for these things, but again, this is really very important to note, okay? Yeah, so this is what I'm talking about. By the time we correct for that, this is what you see on the right, right? You see the more continuous events after correction for this shear wave splitting. So I'm not going to say much about this because you may not capture the full message around imaging because there is so much. Imaging alone can take us about an hour to look into when we are looking at the earth model building and then the velocity model building. But one of the things to note is that when we are imaging PP data and PS data, it's quite, we handle these things differently. And certain things, certain assumptions are usually being made in the PNS model, and how this is handled in migration, whether we're using Kirchhoff migration or you're using RTM, reverse time migration. So when we are talking about seismic migration, for those that may not be familiar with this, it is a process basically where we are migrating seismic events from their sort of acquisition recorded locations to their actual subsurface location. That's why we say migration. So we are moving it, we're using the velocities to move them from that location to their true subsurface location. So all the stacks have been showing us are image data sets like this one. So one of the things you then see in this image data immediately is that this is a case study from the North Sea. And this is a reservoir section after what we call pre-stack time migration. Okay, so the PS image section on the right, we can begin to see it helps us to clarify the reflection discontinuities in the reservoir section. Okay, so better than what we can see on the PP on the left. Okay, so it gives us different information. Now I'm going to go into some case studies, and I'm going to wrap up at this point for any further questions. So in the case of a gas cloud, right, Uh, this is a case study as well. And one of the things you can readily see from a narrow azimuth PP data, there's so much that is obscured in this data set. It's wide azimuth PZ, right? And one of the things you can begin to see here is it's obscured. There is a gas cloud here. There is the cartoon here telling us what is going on. For PP, it's not going to transmit through it, okay? And we can even experience, we'll see some sags, okay, right above that, okay? But when we look at the PS, it's able to transmit through this and we can image through the gas cloud very well. So usually this becomes a complementary product for operators. So they can use these two data sets and interpret them together. All right. So they use both interpretations. It complements. No single products have it's got everything. So it complements each other. Okay. So that's one there. The other one is whether there are what we call hydrocarbon indicators or direct hydrocarbon indicators, DHI, right? And there's been situations where if you're just going with PP data historically, we've seen where well campaigns have failed because they drill after spending millions of dollars, depending on the location, spend millions of dollars to drill a well based on a bright spot that they saw on the data, and they've basically made decisions based on that bright spot. But then there is, if they had looked at it on the PS, then that would have been able to tell them whether or not that is a true direct hydrocarbon in the indicator. Okay. So there has been many false bright spots. Okay, that people have, and they've drilled and made decisions of that, and millions invested only to find out that they were not real. Okay, but if they had acquired PS data, they would have been able to get that information and confirm if that is true or not. Okay. The other benefit that multi-component brings as well is in the area of structural enhancement, and that benefit comes from its azimuth, its rich azimuth information, and this you can see on the image here. The left is the total streamer data. Now, one of the things that you could get fooled by with the total streamer data is the high frequency, loose, crisp, and in time because it's just high frequency, but the same contents are present in the OBC, but you see it's a bit low frequency rich on the OBC data. But then one of the things you begin to see is the distinct nature of the structural components of that which you cannot delineate on the total streamer. Really difficult to know where the base, where the top of those structures are, but you can see that clearly because of the low frequency nature of the OBC. Again, this is another example where there was the challenge here on the tow streamer was poor seismic over the crest, which you can see. And you see a lot of multiple contamination as well. Okay. But then when you look at the toads, when you look at the OBC PZ data, you begin to see those fault definition. Now, this makes a lot of difference if you are drilling a well. But imagine if decisions are being made on this, they wouldn't have seen those faults. Okay, they wouldn't have seen those faults. They could be drilling through a fault or any of those things. So again, you could begin to see the minute sort of details that you are beginning to see. This was their target, and you can see that flat spot here, if you would call it that way, you can see, and that is not even being imaged properly here. But there are more informations being brought here about the faulting system and trapping system for this data. So in summary, again, when we're talking about, so I've basically just touched on some of the key principles here on multi-component seismic processing. So beyond the P wave, which we've traditionally seen in the industry, we're seeing that with bringing more of the shear wave component, there is more that we can then begin to bring out in our reservoir, either reservoir characterization or in the near surface characterization. So two benefits there, both for the near surface characterization and the reservoir characterization. Thank you.
Thank you so much, sir, for the wonderful presentation. I'm sure that we all learned a lot today. I've learned so many things that I have not even heard before, and it interests me, and I'm going to do further research, and I'm sure that every one of us here is going to do the same too. So please, if you have any question, please, I want those people that have questions to use the raise hand button. Then I'll call on you to speak. I
Thank you
think,
very much.
Joshua, you have a question. So please unmute yourself and speak. Okay, so before Joshua will talk, I think there's a question from Paul Alabi. He said that why does geophone is sensitive to noise than hydrophone? Why is the geophone more sensitive to noise than hydrophone?
Okay, so number one is in the environment, right? And it's really about the sensitivity of the instruments and what they measure, right? So you see a lot of the ground rolls and surface waves being picked up more on the geophones than on the hydrophones. They don't pick that up. It's not sensitive to that, right? So it's really around the sensitivity of the instruments. One of the things I didn't really, maybe I should have included that is how the geophones are sort of designed, but it's really in the sensitivities between the two, and then what they record. So what they record is different. So a lot of the surface waves are picked up more by the geophone. So those sort of noise, surface noise, either the rallying waves or the ground rolls, you see a lot of that on the Z component, which makes it a lot very noisy. So you have to do more cleaning the geophone up compared to the hydrophone. Does that answer your question?
Okay, please. Thank you, sir. All right. Okay. Joshua is asking that those multi-component. I'm sorry.
Yes, it does. Yes, I got that question.
Okay.
So that is where you see the benefits of the shear wave as well. Especially when you have pinch outs and it's in terms of I'm trying to look for the right terminology now within the seismic bandwidth of what can be resolved by the seismic, but with multi-component, you can begin to see. There are some data sets. I wish we had show rights and things like that. There are some nice ones you would like to print and just put on your wall, because you will just see you will see it resolves the internal architecture of the reservoir, where if you do time slices, you begin to see those internal events that with just the P wave or the tow streamer data you wouldn't have been able to resolve, because it's just outside the bandwidth of resolution for that sort of thin layer. But with multi-component, you are getting more. Maybe not everything, because even with that as well, it depends on whether you're acquiring a high density survey and whether you're processing to 4 milliseconds or you're processing to 2 milliseconds, which is high resolution processing. So a lot of things come into the factor as well in terms of what you're resolving, and then the velocity model building, which I didn't touch on today as well. Yeah.
Thank you, sir. Okay, when you were talking about the common midpoint and the common conversion, or is it CCP, the CMP and the CCP?
Yeah.
So you mentioned something about we have to like know our target to know the kind of configuration that we want to adopt. So how are we going to? I thought we will try to from this configuration is when you know the configuration of the subsurface. So how are you going to know before using the configuration that okay, this is the one I want to use for you know
Okay. So before we
refining?
go how to acquire any seismic data, good question. There's what we call survey design and modeling. A survey design and modeling where you look into the acquisition configuration to determine whether you're able to illuminate and image your targets. Okay, so that comes into play as well before you even go out to acquire data. That has to be done to see what configurations would help you as the operator meet your objective. So a lot of things come into that factor. There is the geophysics, there is what the geophysicists like us want to do. You want to get the best, but then you have to balance that with what your management is willing to pay for. Okay, so you have different scenarios of what you can achieve in terms of that configuration before you go out to shoot, and make sure that if you are shooting that data, when you then process, you're able to meet that objective. Basically, does that answer your question, Rodia?
Yes, sir. Yes, sir.
Yes.
Thank you, sir.
So there's what we call survey design and modeling. So you do things like illumination studies, things like that. That could be another thing. Maybe you could bring someone to talk to you about that. So that happens even before they decide to even shoot seismic. So that has to be done. The configuration has to be done. Then that is what the seismic acquisition company then executes.
Okay, sir. Thank you so much. Please, does anyone have any question? Okay, so I think if no one has a question, there's one question on the Google form that says that you graduated from Federal University of Technology, Akure. Would you like to share your journey with us, like how you ended up in Shalom VJ, just tell us your story briefly, sir. Thank you.
How did I end up in Schlumberger? Okay. What's my story? So I had my internship with Schlumberger. So I had my internship with Schlumberger, and I was told I did well. And so when I was serving, the opportunity came up, and for them to hire, there was this hiring thing, recruiting thing that was going on. So I attended, I was called. So one of the things that happened is I had built rapport with the people I had the opportunity of working with while I was an intern, and that person just called me that there was an opportunity, so I had to travel down, and it so happened that the opportunity was to have a Nigerian person work abroad. Okay, but the space had been filled, but they were impressed with my interview, and so they made opportunity for me to still travel, and there was a space in Malaysia, and that was how I started my career in Malaysia, not in Nigeria. Okay. Yes, it's been an exciting journey, and I think some of the key things for yourselves as well is you need to start building the industry connections network, maximize conferences was one of the things I did as well. I presented at the NAPI International Conference. Back then, it was done in Abuja, in Nigeria, and northern part of Nigeria. And I presented that conference. Usually, you don't have students present such international conference back then, but I did that, and that was in collaboration with some people in the industry that I allowed them to mentor me. So when I had the presentation, it was something they didn't expect to see from a student, and so it was really big, and I was really excited about that as well. And from there, I started getting visibility also within the industry. Yeah, that's what I can say, Rodiat. But there is definitely a lot I've learned, but yeah, no knowledge is lost is what I can say. Everything you can implement it. It makes you a rounded geophysicist, to be honest. Yeah.
Thank you, sir. Thank you for your response. So we should show up and be active. It's very important. All these
Yes.
professional organizations and conferences. Okay.
Yes, it is.
We have a question from Rezik. I'm so sorry, your name. She said that how she wonders how we get different types of azimuth in the acquisition type. Is it depending on how the way the acquisition was acquired or the way the data we used in the same acquisition?
Yeah,
Do you
it's
get the question,
dependent
sir?
on. Yeah, I understand. So it's all dependent on how the data is acquired. Okay. So that depends on, again, I told you a lot of factors come into play when you're designing your survey. Uh, but again, yes, a lot of that depends on what you get depends on your acquisition. Now, there are times as well in processing where, for example, you've got a tool streamer data and you have a multi-component data that is rich azimuth, full azimuth, and you're trying to match the two. There are some cases where they want to do, you see some very crazy things people want to do in the industry. Maybe they want to do a 4D of tool streamer to a multi-component. So one of the things you might want to do is to match the two. So that means you may have to drop a lot of traces, a lot of data that is not within that azimuth, just for you to match those. So again, that is in processing, but yes, a lot of that is the difference in azimuth that you see comes mainly from how the data is acquired and how they want the data processed as well.
Thank you, sir. So Ariola Joshua asked that can machine learning be implemented in this multi-seismic component technology in any way?
Can what?
Machine learning
Yes,
or
of
artificial
course.
intelligence.
Yes, that's the future. Machine learning is the future. So if you in the industry that we have today, for you to call yourself a geophysicist, you need to have that in your as one of the things you must be able to offer. Yes, that's the future of a geoscientist in the industry today, machine learning.
Thank you, sir. So we have another question from Paul Alabi. He said, what is the success probability of multi-component seismic technology compared to the traditional method of seismic data acquisition?
What is the success probability? It depends on the setting, it depends on the complexity, it depends on the problem you're trying to solve. Okay, it depends on the problem you're trying to solve. So there are, the truth is that the very simple place where you can get hydrocarbon today, or some of the things we are now looking at in new energy transition, carbon storage, and things like that. Okay. In terms of the complexity of what they are trying to achieve in being able to understand the containment, right, of that reservoir and being able to hold CO2. Now they need to do a lot of data screening and characterization of that. Now they need very good data. They need very good data. And so that depends on the geology and the complexity of what you're looking at. There are some places that may not need that for now. Okay, and so you acquiring multi-components might not bring a lot of value. Okay, there are still people acquiring tool streamer today. Like I said, when you look at the market today, more than 50% is still tool streamer market, the seismic. But then we are seeing people picking that because all of that is cost as well. Multi-component seismic costs more, right? It costs more. It's more expensive. But that's why we're beginning to see this hybrid thing that people are now testing as well. So it's not straightforward. It depends on what you're trying to resolve. But when you have a complex geology, in very complex geologies, where tool streamer may have failed and all that, then the answer may be multi-component seismic. Okay, but where you have complex geology, of course, you know that your tool streamer is narrow azimuth, even though they try to mimic. So one of the things you find as well is they try to mimic the rich azimuth survey by acquiring what we call wide azimuth surveys, or PGS will call it something else. They call it GeoStreamer X, where they go in different azimuths, and that is quite expensive as well. So it depends on what you're trying. So when you're talking about the success probability, it depends on a lot of those factors. And there are people who just acquire ToStreamer now, and then when they've made money on their production, they can come back and acquire OBN or acquire multi-components. But you find that maybe they do low cost for exploration, but then when they are producing and they need to understand, characterize the lithology and fluid better, when they encounter problems on their production, for example, then they might begin to look more in the way of multi-components.
Thank you very much, sir. If there are no questions, I want to say we have come to the end of this course, and we want to really thank you, sir, for taking time out of your evening to lecture us on this course. We really appreciate your effort. Thank you, sir. Thank you so much. And I want to thank all the participants for attending. We'll send your certificates to you. Thank you so much, everyone, and have a good evening.
Thank you all. Thank you, Rodia.